So everybody, let's welcome Hao Zhu. Hao is actually joining us from the US, who arrived just the day before yesterday, right?
Yeah.
It's a pleasure to have Hao with us. He's a professor at the University of Texas at Austin. And she had her bachelor's degree from Tsinghua, and then you did your PhD also with Yanakis at the University of Minnesota, right?
Right.
With a very strong group
Another famous Greek. Sorry.
And we have been following your work for quite some time, and we would very much like now to hear firsthand what you have to talk to us about.
Yeah. Thank you, everyone. Good afternoon, and thank you, Spiros and Gerard, for inviting me. I came here from 40 degrees temperature for at least 20 days in Texas, so this is great. And I guess I brought the sunshine in a way, so yeah, glad to be here. So I know that yesterday you guys have a very a full day on machine learning. So my plan today is to give a little bit background related to what I'm going to present, but it's mainly on some of my research work recently. So hopefully it's not going to be too, the level is going to not be too different. So I would like to thank my students and also US National Science Foundation for the support. So let's get started. So we have witnessed a surge of interest in artificial intelligence, AI, and machine learning. So they're envisioned to be used for a variety of tasks in energy systems. And this is thanks to the unprecedented opportunities offered by different types of data sources, as you can see from here. So the question I would like to explore today is how to harness the power of machine learning to tackle problem-specific challenges for real-time power system decision-making. And we will see that the power system engineering expertise will be, or domain knowledge will be very important in bridging machine learning with power system problems. So just to get started, as an example, let's look at this power system stability problem, how we can use past operating data to know whether the system is stable or not. So these are the data samples you are given with, like it's 5 instances, and each instance has a voltage measurement, an angle measurement, and then we know that whether the system is stable or not. Okay, so you get 3 samples that are not stable and 2 samples that are stable here. Okay, so this is an interesting application people explored a decade ago. So how we can try to do that task? It's actually a binary classification problem, right? We just want to know whether it is stable or not. So just to get terminology straight, every row we call it the training set sample. It's a data sample. And then for every row, there are 2 inputs, which we call the futures. They're also called covariance or regressors from statistics. And then what we want to predict is called target variable y. And it's binary, stable or not. So that's why it's a binary classification. So you can have even more output targets that you want to predict. So for example, you can predict whether it's angular stable or whether it's voltage stable. So this becomes a multi-label output case. But in addition, you can also have a continuous output, and it can be a stability score from 1 to 100, and this becomes a regression problem in general. Okay, so what would be the first type of solution people thought about to address it? And this is called decision tree. Okay, so you can build this tree here. It's a simple rule based on the angle. So why did I pick the angle? It just seems like there's some kind of division there based on the angle variable. Okay, so the tree says that if the angle is less than 0.5, then it is stable. If it's bigger than that, it is not stable. So this is kind of intuitive based on our knowledge of power systems dynamics, right? So how good this model works, okay? Can we visualize it? Yes. So you can plot these samples into a 2-dimensional space, right? And then the horizontal one is the angle. So everyone can see that this decision here becomes a straight line, right? So everywhere below this line is stable, and above it is unstable. And then the red is actually the samples that are originally unstable, and then the green ones are the ones that are stable. So how is this one doing? Not good? Okay, what's the accuracy you think here? How many stable, how many good data points that samples it have achieved? 3 out of 5, right? And then because basically we are saying everything below this line is green, right? Which is not the case. Well, the only one above it is correctly identified. Okay, so how can we improve that? What else can we do, you think? Let's get more cut, right? So yes, we can have another cut, meaning that we can have another decision rule, and this is a depth 2 tree, right? So you can pick, first of all, look at the voltage. If the voltage is less than certain threshold, which is 0.95 here, is unstable, and then if it is above that, it is stable, okay? Am I getting better now? What do you think? Yeah, so which ones have I been able to classify successfully here? 4 out of 5, right? So this is to say that if you build more and more, so specifically the bottom left one is being correctly classified, okay? So if we build more and more layers, or more and more cut here, then we can successfully classify every 5 data points here, okay? So this is the first step, usually people from data mining to approach classification problem. It's called decision tree. It's related to like random forest or ensemble learning. So it's a very powerful technique. But then what we also want to ask is can we do it more strategically? Can we think about partition this space with different type of curves? Because decision tree only allows me to cut it horizontally or vertically, right? So how about we use what's called a linear rule? So this is the rule here, and everyone can see that it is basically becomes a straight line in this 2-dimensional space, right? So what am I saying using this linear classifier? Everything left of this line is stable, unstable? It's actually unstable, right? And then everything right of it is stable, okay? So this is a single rule here compared to the depth 2 tree earlier, right? And I'm having the same accuracy as before, okay? So this is the basic idea of having a linear classifier. And so the question is now, is linear good enough? I'm not having 100%, right? So there's some space to improve. What do you see as a better one? What can be better than the linear one I'm showing here? Any guess? Nonlinear, yes. As engineers, we don't like to go to nonlinear domain. Always like to linearize the system, but sometimes they are better for the reason that you can see. So what kind of nonlinear curve would you want to have to classify them? What can be possible? Yeah, it can be a circle, quadratic parabola facing down, right? So whenever we explore more higher dimensional embedding, then we have a better chance to improve the accuracy. So this is exactly the reason that we go to nonlinear functions when we look at machine learning models, okay? So this is a simple example, and so for the first 10-15 minutes, I would like to put another primer. I know there's probably a lot of background yesterday, so feel free to let me know if this is boring. So in general, when we set up machine learning, we look at supervised learning as the example that you have seen, okay? Which means that you have a pair, x and y, and x is the input feature and y is the target, okay? So based on the type of value that y takes, it can be classification, meaning y is discrete, or it can be regression, meaning it is a continuous output, okay? So this is a typical joint distribution, a Gaussian distribution, as you can see here, okay? So what is the challenge, or what's the difference between machine learning and statistics? So we don't know this joint distribution, okay? We don't have the analytical formula for it. So that's why we have to go from data, or what we just call data samples, okay? And then these are the pairs of a sampling of this joint distribution, and I just told you about these terms here. So sorry, just to relate, when you don't know about YK or you know a subset of YK, this is called unsupervised learning or semi-supervised learning, okay? When you have these data samples generated from a dynamic systems like Flora just talked about, when there are system dynamics, internal dynamics, as in a control system, this is the subdivision of reinforcement learning. So a lot of them are actually related as on the basis of supervised learning, and that's why I'm focusing on that. So the holy grail question that we ask in supervised learning is how do we try to optimize this mapping from X to Y, okay? So every problem that you have seen, or the example you have seen so far is that, oh, we have an X. What is corresponding Y? So it's a function, as we know from mathematics, right? So this function, let's call it F. And then when you are given an X, the corresponding F of X is called the predicted value, okay? Or the prediction. And to quantify how good the prediction is, we need some loss function, okay? So it's a function with the actual Y and the predicted Y as the input. And you can see that this is coming from some kind of norm quantification. So if Y is continuous, then you can use the P norm of the differences. And if it is classification problem, as we have seen, you can use what's called cross-entropy loss or hinge loss, depending on what kind of optimization method you want to get into. Okay, so a lot of machine learning problems eventually boils down to picking this loss function or how you design this loss function here. Okay, so once we are given the loss function, you can say that the optimal F or the F star is the one that minimizes the expected loss. Okay, because I just told you X and Y are joint distribution, so you can find the expectation of this loss function defined here. Okay, so this F comes from certain type of function groups, which we will describe later. But what was the issue again in machine learning? We don't have the distribution, right? Therefore, instead of using the actual expected value, we take the approximation or the counterpart of that when we don't have the actual distribution or when we only have the data samples. And this is called the sample mean. Okay? So instead of expectation, I took this actual loss value, averaged across all the K samples that I'm given with, and this is the actual F that I'm looking at. Okay? So this is exactly what a lot of machine learning people, they analyze from a generalization point of view, how good it's between F star and F hat, because we know this sample estimator scales with the number of samples, right? Anyone knows how this accuracy usually scale with? So the more samples that you have,
exponentially?
It's actually also a decreasing rate, but it's more specifically 1 over K. Okay, so the more samples, it's not as fast as exponential. Yeah. Okay, good point. Yeah, so there's a huge literature on how to quantify the difference between this actual F star that we want and F hat based on the generalization results. Okay, now everyone is good on the sample loss so far. So this is called average loss, by the way. Okay. So now let's look at what kind of F can we search for. How easy is it to find a function? How many functions do we have? How many possible function forms can we have in this world? Infinite? Infinite of infinite, right? For even polynomials, you can have infinite number of them, right? So the key here to help our search is to do parameterization. Okay, so we're not allowed to have any function we want. We always focus on a certain class of functions. Okay, so I told you about the linear functions. We all know what linear functions is constructed, right? We have this W transpose X plus W0, and this is called the weight parameters. Okay, so they're simple, so you can do like a least squares or least absolute value estimation for regression, or you can do linear logistic regression or linear support vector machines for classification. And this is the perfect example. It's like a support vector machine here. When you have the linear rule, it works out very well, right? But we know our data and the real world functions are not, the real world scenarios are not perfect. We need nonlinear functions. So usually people pick nonlinear functions, as we have seen in the stability example, for better prediction. So you can use polynomials, Gaussian processes, and then kernel learnings, meaning that F is in the Hilbert space for some kind of kernel functions. And then most popularly neural networks, which is what I'm going to focus on more today. Okay? So let me also take a side from the function and then talk a little bit about regularization. Okay? So when we have data and we're trying to only minimize loss, there's some issue in that. Okay? Because if we allow the function to be as complicated as possible, we can have zero loss. Okay? But why? If I going back to my example, if I have a 3-depth tree, this is perfectly classified, right? If I have a quadratic function or actually a circle, as people suggested, I can perfectly classify this. Is this what I really care about as in machine learning? So what do I really care about? If not that, zero losses.
The flexibility to predict new points that have not been joined.
Exactly. So this is called generalization, or you want the classifier or this rule, the F, is not working necessarily well on your given data set, but you want it to work well in your future data set. Okay? And there is a very well-known trade-off in that called curse of dimensionality, right? If you fit too well the data you are given with, it might not generalize well. Okay, so because your model is very complicated, it tries to fit so well your given data, and it forget about, oh, sometimes life is simpler. Okay, so this is the trade-off here. So where you can see from this example here, okay, so we have these data sets, like let's say we want to do classification here. The left one is simple, okay, but it's too simple. It's linear. You don't capture a lot of the complicated curvature between the two clusters, okay? But if you want to have perfect classification, let's go to the right one, okay? But is that something visually you feel is appealing to you? Not necessarily, right? There may be some simpler one that still has some kind of error, but can do pretty well, okay? And I just want to say that having zero error is never, for the training part, is never the objective in machine learning. Why? Because there is a very famous example. If you have a total k data samples, then you use a k-1 order polynomials, you can fit perfectly everyone. You can make everyone happy, right? With 2 data samples, you can use a straight line to fit them, right? And then you can make everyone happy. But this is not necessarily good at the generalization phase. So this is why we need regularization. We want to use something to make the model simpler, okay? And this is the regularization term on top of your original loss function there is sometimes a norm of parameter W, okay? And here, the lambda here, add them together, is a positive value to balance between the data fitting and the model complexity. Okay, so if you choose a certain type of norm, for example, for the blue line, then you can say that, oh, I want it to be more smoother, but then I can have a little bit error for the first term. Okay, and the typical choices for this norm can be the L2 norm for the Euclidean norm, basically, for all the W's, and then we can encourage very small W values. Or if you use the entry-wise differences, and then you can encourage this W to be a smooth signal, right? You can imagine that basically the change of W is very small, instead of the value of W is very small, okay? So this second one is very important in like video applications because you want the image to have smooth edges. So this is why it was first used. And then the other one is called the L1 norm, or is related to what known as the lasso estimator. So it is encourage a lot of W to be 0. Okay? So if you think about linear functions, if a lot of weights are 0, then you are selecting certain features and then you are disregarding other features. Okay? So this is the general purpose of regularization. Okay, so with that, I'm going to again talk a little bit about the deep neural network architecture. So we talk about linear function. If instead of linear, so let me just forget about the offset. So originally it's a linear with W transpose X, okay? If I go to the nonlinear one by using what's known as the activation function sigma, it can be sigmoid or tangent H or rule, then we can immediately have nonlinearity. And we all know that I like that because of the better prediction performance or less error here. So neural network is nothing but multiple layers of this linear transformation plus some nonlinear activation. Okay? So it's called feed-forward structure because it's just go one way, that's your data flow. And then the hidden layers are called neurons or units, like it's trying to represent in the old days, like what we view how brain works. But then the power of neural network is once it goes to nonlinear, it can approximate or represent the functions that we'd like. For example, 2 layers neural net can express all continuous functions. And then if you have 3 layers, it can even be, actually I'm missing something here, it can be discontinuous as well, okay? So this is the power of expressiveness in neural networks. So with that, I will have one slide on why we like neural networks. So think about that, again, we're going to the problem having minimized the loss function plus the regularization terms. It's nonlinear. It's actually a non-convex problem to find these W's. But then everyone knows that even for non-convex optimization, we can go ahead to use the gradient-based method to solve it. And there is a concern about non-global optimality when you have non-convex optimization, but there's a famous paper to say that in practice, this might not be a concern. So yeah, there are a lot of recent development on machine learning is trying to understand where you can tackle this non-convex or this difficult landscape, okay? So finally, the reason that we like neural network computationally is the fast solution here, okay? And it's specifically enabled by something we know very well from calculators as the train rule, okay? So to calculate this gradient, although it's multiple layers, it has a very fast way to do the so-called back propagation, right? As long as you start from, so actually the top is the final layer. And yes, the top is the final layer. As long as you start from the top layer, and then you can quickly propagate down using the partial derivatives or train rules to find these gradients for each W, even though it is the W sits in some hidden layers, okay? So this is the computation reason why we like neural networks. Okay, I'm almost done, I promise you, on the general DNN here, okay? So now, what is the reason we don't like neural networks? Have you heard about, like, something, yeah?
They're black box?
They're black box, yeah, they don't have physics intuitions, right? And also, like, even though there's a computation benefits, the general neural networks has some issue that it's just too large, and sometimes you need to have really deep ones. And related to what's brought up, like, it's it doesn't have physics intuitions. When it doesn't work, you don't know why, because it's just so deep, right? It's just hidden somewhere, maybe having some issue that we don't know, okay? So there is a huge concern about the complexity of neural networks, okay, when it goes very deep, okay? Because every layer you have new weights, right? If your input and output has many, many features, and then which means that every layer is the number of input variables multiplied by the number of output variables. And this can quickly scale up, okay? So what is the idea here to tackle that? Is something, as electrical engineers, we know very well. It's actually filter, okay? We learn filter in the beginning of signal processing, right? So we have the temporal filter, right? Instead of having everyone to say your weights are different, let's reuse the weights in a way. And this is the basic idea of filtering, right? So that all the input, like you have an impulse response, that's your filter, right, is used for every input time lag, basically. And then this first idea, recurrent neural network, is exactly trying to explore on that, okay? So this is used for like temporal signals like speech or text. So you reuse the filter for the input time sequence, basically. Okay, so in addition to temporal filter, we can have spatial filter, right? And this is actually more well known as convolutional neural net. And where do you think this is the best application to be? Image, right? Because image is a two-dimensional representation, and then you can use this to filter a patch from the original image. And that's the same idea. It's a two-dimensional filter, basically. Okay? So the one that I'm going to focus on today is called graph filter. Okay? So it's the same idea that I don't want everyone to say, oh, yeah, your weight is all over the place. When your input future is organized on a graph, okay, you can say that this filter is based on the connectivity of the graph. Okay? So this input future, the linear transformation, would only happens when the two nodes are connected. And this is the key idea of graph filter or graph neural net in reducing the complexity. Okay, so I will talk a little bit more on the last one today. With that, the three problems we're going to look at today is how to use topology to tackle the complexity in large-scale power systems, specifically using the graph neural net to simplify the neural network model complexity. And then the second one, which is also related to power system physics, is that we want to think about the risk-aware measures in the learning problem, which is something I touched upon very briefly originally, that the loss function that we typically use in neural net is the average of everything, okay? But for power system operations, sometimes we don't care about the average case, we care about the extreme case or the worst case, okay? So we will see that how you can redefine the loss function or how can you define other metrics to focus on the worst case scenarios. Finally, if I have time, I'm going to touch upon an application in reinforcement learning where you see that the representation of the model will be very important in allowing for efficient search. Okay, so before that, any questions or any quick comments? Yeah.
So is filter just couple layers of neural networks?
So the filter, yes, good point. So let me be a little bit specific. So you can think of neural net whenever you have this linear transformation W is a filter, okay? Or it's part of where you're going to insert a filter. You're going to repeat that, okay? So it's the linear part, okay? So basically you can think of that instead of having a whole W that is the same dimension as my input X, you can use a small patch W to go through, to scan through the X instead, okay? So this is the idea of like, say for example, the recurrent neural net. So it's going to scan through the input time series. It's not going to grow with the number of time slots that you have, okay? Good point. Similar in the CNN, well, your original will be 248 by 248, for example, as an image, but instead you use 16 by 16 sized patches to scan through the image. Okay? Yeah?
Yeah, about the graph filter, so how do you choose between having a shallow network fully connected or having a deep network with your, like, is it just a matter of experimenting and seeing what works? Or is there some intuition for different problems? Or,
yes. There are. Great question. So it's going to be very important when I talk about actual GNN later. Okay, so I will keep the answer later. Thank you. All right, so in the interest of time, let me go to the first problem where I promise you that the topology information can be used to improve or make the model simpler. Okay, but of course there's a question of how. So the specific application I'm looking at is optimal power flow. Okay, and there's a huge interest on that from academia on using machine learning to solve optimal power flow. We can have a separate debate when we have a glass of wine on whether we should do it or not. But I just want to say that use that example where you can see the graph neural net can be applied. Okay. So how do we solve for OPF now? You have input data about system model, and you pick your favorite OPF solver. Usually it's an iterative optimization solver, and you find the output, right? And whenever there's a varying of your input operating conditions, then you resolve it again. So the idea here is that once I have this input and output pairs, that's my samples, right? Can I build a neural net or function f to map from the input to output? So that's the basic idea here. So computing this in the real time, once you have this neural net, it's very simple. As I said, it's a feed-forward structure. So you can very easily compute the corresponding output when the new varying input is changed, once you have this input-output mapping. So I know that this is only a selective part of existing work. People have thought about using this to warm-stat, iterative optimization solver. And then there are a lot of interest to use like connections between duality or KKT conditions to make the problem more feasible or better, including some work by Spiros, a very interesting one that we've been studying recently. So I want to point out that almost all this work built upon this, what I call the fully connected neural net, or this basic version of neural net. So one question we feel is that whenever there's some variation in the input in the grid topology, we don't know necessarily how to adapt it, okay? But we know that grid topology could change on a daily basis or within an operational horizon, right? So the one promise of using the graph learning is to tackle that, as you will see later on. Okay, so the focus here is, can we use the graph learning approach for reducing the complexity, the model complexity, and also to achieve topology adaptivity? So let me jump into the formulation. I'm sure you all have enjoyed learning that in your first or the first graduate level power system classes, right? So think about like I have n number of nodes in my power grid, and this is a basic version of AC OPF. And it might be slightly different from the formulation you use because I'm looking at optimizing the injections of every node, so PI and QI. Okay, so we know that it minimizes the cost subject to power flow constraint, which can be written as this complex format, and also voltage, power, and limits. And the last one is actually the line flow limits as well. So if I want to set up the learning problem, right? So the input, oh, by the way, so why is only having the injection? Because the loads or the non-flexible part has been set up in these limits in a way, right? We know that we can basically use the load injection to know what is the corresponding actual range of the input. So when a node has no flexibility, the upper-lower limits will be the same thing, right? Okay, so now in this achieving for a neural net or solving neural net, we have every node has different inputs, which are basically the limits that we need to specify for PQ injection. And also, we need to specify the cost model. So it can be a simple quadratic cost. It can be also piecewise linear, right? So the nodal output we want to predict, or the target, as I was speaking, is the optimal PQ here, okay? So what is the issue here? Both of these scale with the number of nodes, n, right? And as I told you earlier, if I use a simple fully connected neural net, it means that every layer will scale with the product of the number of input and number of output, okay? So in terms of scaling with n, the number of nodes is n squared, Okay? So that's the scaling for every layer. So this is the number of parameters that I need to train or I need to learn in every layer. So we know power system is a graph, right? So we could use the graph topology in this learning process. And people have explored it, but then they're not from power engineering background. They just simply use the graph topology and they say, oh, let me predict the optimal P and Q here, okay? But there's an issue in that, which is going back to Flora's question, is you cannot just set up any output labels to predict when you use a graph neural net. You want the output to have topology dependency, or has what's called locality property, okay? So you want it to have some kind of connections when the two nodes are connected, okay? So it's not just, so do we think P and Q for any two nodes that are physically connected will be similar? Have anyone look at the OPF solution? Do you think the PQ injection should look alike for two nodes next to each other? Not necessarily, right? It depends on the generator model, right? The cost model. So this is not the case. There was no physics intuition in directly applying graph learning for this OPF setting. But what can be topology dependent? Or what kind of outputs could have the similarity when you look through the connectivity of the nodes? Yeah. Yes, the voltage definitely. Okay, so the voltage magnitude, we know that it looks very similar. It's localized, right? So actually, this is the second part, which I should have brought it earlier, because for voltage magnitude, it's based on like using an approximation model is B inverse times Q, where B is the graph B-bus matrix. Well, B-bus is also known as graph Laplacian, and that explains why this topology dependence or localized voltage. Okay, there's something else which I already showed in the slides, as you can see here, which is the dual variables from solving the OPF problem, known as the locational marginal price. Okay, so I'm only using a simple DC OPF formulation here, but you can see that from this optimality condition, it is related to the line congestion variable mu minus mu. Basically, for every line flow, we have a pair of multipliers, and we know that the locationality of the price, if we don't have a line flow constraint, it's marginal price, right? But when we introduce line flow constraint, it becomes dependent on the location, and that dependency coming based on the congestion pattern. Basically, while you have congestion, then the corresponding mu of these lines will be non-zero, and you can see that they're affecting the LMP pi star here based on this S transpose matrix, and S is known as injection shift factors, right? It is again related to the B-bus matrix. So this is why these two quantities are location topology dependent or like localized, okay? So specifically, you can think of them generated from this eigenspace of B-bus. So if you think about you do eigendecomposition of the B matrix here, then they share the same subspace as the eigenspace. Okay? Yeah?
Can I ask something? How do we determine the Q in this setup? We are solving this COPF, so no idea about Q.
Yes, it's a great point. So yes, the delta Q here, the actual optimal solution may not be known, but then the mapping, like this transformation being inverse, is the key here, why it has the locational dependency. So in real-world power systems, even if you didn't solve the OPF, we know that the voltage will look similar in the network. So it's mainly from that reason as well. So even the delta Q can change a little bit. This kind of subspace lying or the locality property still holds.
So using delta V, we are reaching to delta Q.
We're using delta Q's mapping to generate delta V to corroborate that there is a localized property there. Okay.
And this formulation, PV and PQ buses are both formulated, right? Or all of them are PQ buses?
So we're thinking delta Q to be given, but yes, there are both PV and PQ buses in the system. Yeah. Yeah.
If we see in the LV grid, then if there is cables, underground cables,
Yeah.
then the effect of P on V is more
That's true. Yeah. So we first focus on the high voltage system, but even if if P is affecting voltage, it's also related to the inverse of the counterpart of the B bus for the line resistance part. So in a linearized DC flow model, you can also establish that there is a similar type of graph Laplacian matrix to map from the P perturbation to the V perturbation as well.
And by the B bus matrix, is it the susceptance part of the Y bus matrix?
Yes, yes. Or you can think of it as a linearization of this decoupled power flow model. Okay? Yeah, good point. All right, so I don't think I need to convince you about this is the case. I'm sure that you, like me, you have tried to look at the real price map once in a while just to understand how it is. And it is definitely having this locational dependence. And this is the type of graph outputs, as we were saying. We cannot just pick any outputs. We have to pick the type of outputs to predict. That depends on the topology, okay? That depends on the location, or has this location-based similarity. Yeah?
I have a very quick question, just to clarify. In the previous slide, so in your work, we're assuming that I think that with the equations involving the injection shift factors, those correspond to the congestion component of the LMPs. So
right.
You assume that these mu J's are spatially correlated.
I'm assuming not the mu's are actually correlated, but because of the transformation. So I think this is a good one to clarify with the earlier question about the delta Q and part. It's only because the mapping, the S transpose there, it makes that they have locational similarity, even if the input mu are totally random. Okay, yeah. Okay. Yeah, so let me just quickly explain on this graph neural net idea, how it is different from the typical neural net that you have seen. So let's say that the input is formed by the matrix. So we know there are n nodes, right? So input is a matrix n by d. So if it is 6 nodes here, then it's a 6 by d matrix. So each row is the input futures, the limits, and the cost model that I need to as input. Okay, so this is my input x0 here for the first layer. Every layer of GNN is still a linear transformation with nonlinear activation. The only difference is, since the input is a matrix, I can do linear transformation from both sides. Okay, I will focus on the left-hand side, or the left side, which is this WL matrix. Okay, it is exactly 6 by 6, right, for matching the dimension. And this is the type of sparse structure for the W matrix. Okay, what does it look like? You have seen this type of sparse structure in power systems, right? Yes, it's Y bus or B bus, right? So it only has non-zero weights when the two nodes are connected. And this is exactly where we have the graph filter. So basically, when you multiply W with the input, it aggregates the connected nodes. So as shown here with the shaded area for node 3, it first aggregates 2, 6, 4 into the update for node 3. Okay, and then if you have 2 layers, then you will include every node after this second layer. Okay, so this is exactly where I'm reusing the nodes. Why? Because now the number of weights do not increase so rapidly with n. Okay, so just to mention that on the right side of X, I'm also having a filter, and you can think of this as your typical neural network filter or weights. Okay, so it's going to be a d by 1 vector, d by d prime matrix. So it is your typical filter for exploring higher dimensional representation. So I want to mention that GNN ideas, because of this topology dependency, it has been also exploited for fault localization. Okay, you can imagine that, okay, the input futures will matter most for the nodes that are experiencing the fault. Okay, so it's a very unique way to organize your structure, your data structure when they are depending on the nodes. But then what you're really looking for is like the output should depend on the topology or having this locality property. Okay. So with that, we have a big reduction in the number of nodes, parameters for every layer. Okay, so one thing about power network is that it's typically sparse. So the number of edges scale with number of nodes, right? So in the matrix W, the non-zero entries will scale with the number of nodes. So it's a scaling of n, okay? But then for the other side, the H of L, it will depending on how much higher dimension you want to explore, but it's regardless of big N, the number of nodes in the system, okay? So we reduced from a quadratic scaling to a linear scaling for this GNN idea, okay? So this may not seem too large, but when you have thousands of nodes, that's a huge parameter number reduction here. Okay, so I still want to go back to connect to the physics problem here. So even if I have predicted LMP and also the voltage magnitude, I'm still looking for generating the solutions from the original power flow or OPF outputs, right? And if you take in power system operations, you know that it's not impossible, right? Because from the economics, once you have the LMP, you know what's going to be the optimal nodal injection as a PI, right? And if I have the PI injection everywhere, it is possible to use this input PI to do some kind of decoupled power flow approximation to find the angles everywhere, okay? And then, so this is like the type of output structures that we have. So from the input x0, the input futures, we do the GNN mapping, find this function f mapping, and trying to predict the pi hat, which is the LMP prediction, and then the v hat, which is voltage magnitude prediction, okay? So once we pass through the LMP prediction into the first flow here, then we can also find some kind of approximate angle in a way, and that can help us solve the power flow as in terms of line flow apparent power, basically, okay? So why we are doing this? So this is to say that not only I can predict these quantities, I can use them for my regularization, because as I mentioned, the regularization will be helpful to further reduce model complexity. Specifically, we want to make sure that the AC feasibility or the line flow limit will be improved after using this regularization, okay? So without regularization, we know that basically we're looking at the loss function, which I said for continuous variables, we're using L2 norm. So this is the L2 norm for the predicted pi, and then L2 norm for the predicted voltage. Yes, there's some oscillation here, interference. Yeah, so you can do that as your loss function. We also included infinity norm for the LMP part based on our experience. Like voltage prediction is much more accurate. We know that voltage is in a pretty small range, basically, right? So the infinity norm, as we know, is the maximum difference in all the entries. It can help to reduce certain like large variability in the LMP prediction case. But then, as I mentioned, we have the network-wide line limit constraint, or the constraint on the line apparent flow as one of the, sorry about another typo here, needs to be maintained, okay? So in addition to this direct prediction loss function, we can also add a regularization term, which is basically using the previous flow here. I can first calculate the predicted line apparent power, and then trying to regularize based on the deviation of that line apparent power to its limit. Okay, so it's trying to ensure AC feasibility here, and we call this our FR, the feasibility regularization term. So a good thing about this feasibility regularization that we developed, that is actually a feed-forward structure. So why did I like feed-forward again in your net? Yes, you can compute it quickly, both forward direction and the backward direction for gradient computation. So once we have this architecture that everything's flow in one way, and then you can think of it as part of the neural network architecture, and then you can quickly use, again, like the typical gradient calculation and backpropagation to compute these updates. And I just want to mention that because the predicted V and P can be both feasible through projection, but then the line flow as a network-wide line limits, it requires this kind of more complicated regularization to make it more feasible.
Can I ask something? So S is determined by the power flow, right?
Sorry?
The line flows are determined by the power flow. So how do we backpropagate through the power flow itself?
Right, because we coded the power flow as shown here. So this can be coded through the neural network. Okay, it's not a good approximation per se. It's basically linearized in a way, except for the first one is based on the nodal injection model. Okay, so this can be all coded into part of the neural network.
Okay, as additional layer, but only this operation is.
Exactly.
Okay.
Yeah. Okay. Yeah.
I'm not sure I understand how you translate your physical network to the connectivity in the neural network. So is the width of every layer the number of nodes in the physical network, and then every connectivity always corresponds?
Yeah.
At every feed forward, the connectivity of nodes corresponds to that matrix?
Yes. So we are going to estimate both W and H matrix here as they're the weights basically, and then we use the topology here to say this W should be sparse like that.
So the width of every layer is always the number of nodes in the network?
The width of every layer. So actually, we could think of it more, the width of the layer is the H part. Okay, because W is a fixed dimension. That's the number of nodes.
Okay.
Yeah, but it's a sparse matrix. So the actual number of non-zeros will scale with the number of edges. Yeah. Okay. Yeah.
So maybe I didn't fully capture it. But so why do we use the voltage and the LMP as a result?
Yeah, that's.
Voltage and the angle?
Yeah, it's still mainly because of that. I need one part for real power, one part for reactive power, and then voltage provides the role to infer reactive power, but it can be also a dispatch signal basically. But then what I'm really looking for is like they are topology dependent or localized.
Yeah, but there's voltage magnitude and there's voltage angle, then you can compute basically everything.
That's a good point. So we started with the LMP prediction because we feel like it's more sensitive to the input. So yeah, that's a good point. We didn't, and also it actually allows us to like having a feed-forward structure and then goes to P and then theta. If we directly predict theta, it can go to P, I guess. Yeah.
You have P, you have Q, you have everything.
Right. But I don't know if theta is that similar because it also has like angular differences on every line as well. So theta has some similarity, maybe not as strong as other variables that we look into. Okay, yeah, good point. Okay, so I hope that the reason that you need to look for something that are very similar is accepted for GNN. Yeah.
Can I ask you? Is there a significant trade-off here between the quality of the prediction and the feasibility of the
Yeah, there's a trade-off, yeah. But it's not as bad as we thought. Apparently, the regularization terms mainly helps to avoid certain, helps to accelerate the search process more than trying to reduce the error, actually increase the error of the first term, yeah. Okay, we will see more later on that. Okay. So actually, yes, this is where the part that I want to show some results. So this is the prediction for ACOPF case for 100, around 118 and 1300-ish bus systems. And then we're predicting the normalized mean square error. This is the first three, the pi, V, and G, which is the nodal injection of generators prediction error. So the approaches we compared GNN with the fully connected counterpart, and both of them have the feasibility regularization. Okay, so you can see that in terms of the pi prediction error, it's not too much different among the cases. It's only like for the FCNN, the last two FCNN, when you incorporate the feasibility regularization, it actually reduces the error for pi prediction because of the, I think, the local minimal or some kind of stationarity search-based issues. And for the V, prediction is all very well, and actually the graph one tends to do much better than the fully connected one, because we know probably the V graph locality property is much better in general. And then the last one, so one thing interesting is like when we match from, or when we transfer from the LMP to the power injection. So the first one is LMP, the third one is power injection. Even though the error in LMP are pretty much the same, using feasibility regularization, the power injection prediction is much better. Okay, so you can see the first one is the GNN-based feasibility one, and the third one is FCN-based feasibility one. Okay, so why is that? So LMP has a lot of variability, but then with certain patterns of LMP, they may look similar in terms of error, but then sometimes when you map it to the generation part, then there is a difference, right? We know it's a nonlinear transformation from LMP to the generation output. So interestingly, we realize using the feasibility regularization, the nodal injection prediction actually is much better, although it doesn't change too much in terms of the LMP one. Okay. So the third one is on the feasibility violation, and you see that by using GNN and also by using the proposed feasibility regularization term, the feasibility has improved pretty well. Or it's like it's better when using both of them. Okay, and the last one is the number of parameters. Well, you see a big difference between the case for GNN and the case for FCN, and these are in exponential scale, by the way, for the last plot. Okay, yeah.
Could you please explain this feasibility once again, like this term?
Yeah. So the feasibility is basically to say that I want the line limit to be as active as possible. So once we predict the pi and V, and then we generate the line flow, and then we regularize on the over limit case. And that's the basic idea of the FR here. Okay? So as I mentioned, like in addition to use the GNN to simplify the model structure, in general, when we have the physics intuition like the feasibility, when you introduce it, it helps the search, it helps the computational case as well. So this is generally why using the FR, like especially the feasibility violation is always improved, right? So we have less line flow violation after that term.
So in the equation, your S hat is your predicted
Yes.
value, and what is this bar?
That's the upper limit. Yeah, sorry, I haven't mentioned that clearly earlier. Yeah. So it's basically like a ReLU on that difference. So whenever it's less than that, I don't care. Whenever it's over the limit, I'm trying to reduce that. Yeah.
Basically, you just look at the limits of the line, or is it also the voltage limits?
So the voltage limits, I haven't looked at it. It's mainly the line limits. Voltage limits can be the nodal projection taken care of that. Then the line limits are system-wide dependent. So I have to use this term.
Normal OPF, like we assign a slack bus. So if we compare that with this kind of model, so here the slack bus is like, so the slack bus, do you also predict the values for slack bus, or is it like constant?
I think as long as it's constant in based on the OPF solver, then I don't need to predict it. Yeah.
It is same as the.
Right. Yeah, it's just the nominal value. Yeah. Okay. Yeah.
So just one more question. So I guess like especially for the voltage, compared to other machine learning applications, you have less variations.
Right.
So it's within a very small range.
Yeah.
So how would you compare the accuracy you have in the model?
Yeah, so that's a good point. So there are some kind of scaling that you can do, like in the neural network training part, because if you know the output future has certain range, you can scale on that to make sure it fits -1, 1, right? We know that this is usually easier for predicting continuous functions like sigmoid, like the output will be within that range. So these are the actual values. So indeed, they are not normalized by, like, say, the variability of each of them, and that's why the voltage arrow, the absolute voltage arrow, is better than the LMP one. Okay? Yeah. All right. Yeah.
So when you give the voltage values, so like if you normalize it and if you have a negative, like just you have the same thing but in a negative fashion. But the actual system, that means a lot different.
Oh, you can normalize it around 1, right? So it will be between -0.05 and 0.05. Yeah, yeah. Okay. I want to give something very exciting, which I promised earlier, is the topology adaptivity, okay? Because you can see that because this W now is based on the topology, so whenever you have some line outages, it can quickly adapt, okay? As a first layer, if a line between nodes 3 and 6 are disconnected, for example, then I can just set the corresponding entry in W to be 0, okay? So actually, we had some analysis. I didn't want to get into the details here. We realized that even for some perturbation of topology, the output of price can stay pretty stable. By stable, we mean that it can look pretty similar to the pre-contingency situation. So this is the plot on that for the larger system, I believe. Yeah, the 23 is a DC case, 2300 bus system. And we look into like lines of high capacity or reaching limit. And we disconnect randomly 2 to 4 lines. And it looks like the output here are still having the same distribution. By the way, this is distribution. So the horizontal axis is the LMP, ranging from around 100 to 200 in value. So it turns out that with topology perturbation, the price has some kind of stability. And we have looked into certain analytical massage into this condition to use like matrix perturbation theory and to try to understand why this is the case. It's actually related to the fact that if you think the B as the graph Laplacian matrix, even if you perturb it a little bit, and then the subspace, which means the eigenvectors for B, can still be pretty stable on that, okay? So we have some more analysis, but I don't want to get into that. But I want to show you is how it works whenever there's topology perturbation. So this is the perturbation I mentioned earlier. I disconnect 2 to 4 lines that carrying a lot of power percentage. And then the blue bars here shows what I call the pre-trained performance, meaning that you have the original topology, you train on it, and whenever the disconnection happens, and you set the corresponding W to be 0, and that can give you already working your GNN, okay? So from here, you can see that compared to the original system, especially for the small one, the error would increase a little bit as expected because I haven't used any data from the perturbed system. And it's already in the same like range. For the bigger system, there's a higher increase from the original error performance. However, the transfer part, meaning that if I just use a few number of the new topology samples, okay, and I retrain it, and it was super fast. It took only 3 to 5 epoch, okay? And this is thanks to the stability I mentioned earlier. So even if you have perturbation, as long as the output values still look pretty similar, then using the GNN, you can achieve this new model that is accurate pretty easily. And you can see that after this retraining process, the performance is getting closer to the original system. So in that sense, it can quickly adapt whenever there are topology perturbations in the real system. Okay? Yeah?
So by retraining, you need to run a proper optimal power flow and then insert a new input and output.
That's
so
right.
In this sense, what is the point of doing this machine learning if anyway you need to run the proper LOPF
Yes.
before and then you have this output?
That's a good point. So you do that with the original FCNN2, right? So what is the point here? We realize we can use much less of samples. And we are currently, we haven't taken a close look on that. You can actively search for the samples that you can just use a few to help you to better retrain it. Okay, so there are some process that can help on this resampling procedure. But then, yes, this is still what is needed whenever topology changes.
And this retrained model, if you go back and you switch on the lines back,
Yeah.
Does it still perform good, or it needs
I
to
believe
retrain
so,
again?
because we basically trained from the original by disconnecting the lines, and then if we have to go back, I'm sure like the whole promise here is like whenever topology changes, it can quickly catch up on that, much faster than a model that does not incorporate topology information.
Because typically machine learning models, the problem is that they tend to forget things. So after you retrain, maybe it already like forgot the previous network. So even if you switch on the lines, maybe the performance is worse.
Yeah, we tell the model which lines are on and off. So this information is given. So yeah, but yeah, so actually how to do quick transfer learning, I think, is the whole thing that we cannot beat the optimization solver, because optimization solver does not need to worry about that at all, right? So I know we have to have a debate on whether to use machine learning for OPF or not at some point. Yeah.
How would it look like if you went back to the previous one with the new retrained one?
So I think it would be the same process to do that as well, because this topology, if you go back from any perturber system to the original system, which is the blue line, you see that the similarity is still there. Yeah, so but to answer your question, we haven't actually exploring that. Yeah. Yeah.
Sorry, just a quick comment on that one. So if you look into the reliability indicator of the tables, they are pretty reliable. For the batch case, on average, like very probably a cable for maybe a few years. And also, I think if it's possible to train like multiple cases, like you assume,
Yeah,
okay,
that's true.
this scenario, this cable fails.
Yeah, you can have like multiple nominal topologies, right? And then that will be, so what we really worry about is not like the cables being replaced, it's all like a fault-induced line outage, for example. Yeah, yeah. Yeah, but then that's a good point. And then I think there was a question here. And yeah, Sadi? Yeah.
It just seems so strange that there's so little change in
The price?
Yeah, because I think if you would like open it somewhere and then maybe close somewhere else, and then you could have currents that completely have to be redirected or something.
Right. Yeah. So my take on that is like I'm sure everyone probably have seen the line of work on optimal transmission switching. When transmission system is developed, there's actually some redundancy in that. So switching off lines may not be the end of day scenario in certain cases, and that may be the reason why after perturbation the price is still pretty stable on that. Yeah.
But do you mean that you don't want to switch off lines, but then switch them off?
No, it's only switching off. Yeah, but then transmission switching like also explores the idea of switching off mainly, right? Optimal transmission switching. Yeah.
Are you saying then, like that even when you open the line, that you're not creating like a very big like kind of topological distance between any particular set of lines than there was before? Because like if you have like two like fairly distant parts that have like one line connecting them.
Yeah, we haven't looked into like this kind of critical lines, I guess, scenario. Like yeah, but then yeah, it's mainly based. We picked the lines mainly based on their like capacity. So we pick the lines that are the top high power percentage on it. Yeah. So it would be interesting to actually find certain scenarios. Maybe there's like vastly dramatically different from here, and see how the transfer speed is. Yeah. Yeah. That's a good point. Yeah. Is there some more here? So.
Yeah. Sorry. Question. I just wondered because after the outage itself, your model works pretty fine actually. So
Yes, for the small case, yes. Yeah, the larger one has like a high increase, probably because the original system is pretty low in terms of error. Yeah.
Yeah, but even the small system is 118 bus, right?
Right.
It's not so small. So
Okay.
how many different profiles have you tested? How many different load profiles in this?
Yeah, so we always like do random load perturbation, actually with a very high percentage, like almost 40% of perturbation of the PQ injection, the load demand, to test out this error here.
For each of the nodes separately?
Yes,
In each other?
random perturbation every node, yeah.
So approximately what is your data size, the training data?
You're talking about the number of samples that we use? Tens of thousands, I think.
Tens of thousands.
Yeah, but that's for the nominal case. For the retraining, we use much less of them. Yeah.
Around 100 or?
We are gonna get there, maybe someday. Yeah, okay.
So instead of fault, have you looked at certain network reconfiguration? Because if you look at a MV ring, there are only certain scenarios which are possible.
Right, we haven't looked too much into distribution systems, but this is mainly transmission results. Yeah, that's a good point. Yeah. Okay, so I think I'm not doing too well in time. I know I'm in between you and the lovely break. So I just want to say very quickly that we have explored this idea for emergency operations as well. So for load shedding, basically, as we know that currently load shedding is based on frequency, so it's a uniform load shedding, but there's also an optimization approach for that, right? So basically you can see, where the contingency happens, and you report everything to the control center, and the control center tells everyone, hey, this is how much you need to shed, right? It's like centralized problem that is the current practice. So what we see as the difficulty is the communications. So the communication rates can be slower than what is needed when you have this kind of contingency, right? When you need to quickly restore power balance. So we have come up with some kind of decentralized solution for that using machine learning. It's the same idea as the ML for OPF I told you earlier, but we are specifically saying that every node that needs to shed power can use its local measurements without even waiting for the signal or any input from the control center, using that local feature to predict that. So this is some recent conference work we have done, and then we've seen some good results on that with single line outage. Maybe we'll have more next time. Yeah, so I would love to get on this, maybe 15 minutes if everyone is okay, on this risk-aware part. Okay. So I think it would be an easy transition from transmission to the distribution systems that we are looking. So specifically, it's like what we have seen earlier on this coordination of distributed energy resources, where we're trying to decide on the optimal setting of the inverters. So it's not the demand response part, but it's the optimal reactive power dispatch. And on the distribution part, as mentioned by the earlier talk, the biggest challenge is the lack of frequent and real-time communications. Okay, so there are tons of distributed optimization techniques by the so for example the final tutorial, and we have worked on this a few years ago on using different distributed control, distributed optimization to deal with this communication limitation. But we see that machine learning can also help on that. And it's the same decentralized machine learning idea that I talked to you earlier. So here's a long list of but incomplete line of work on dealing with this. But then the question we're trying to ask is this risk-aware component. Okay, so this comes to the second part that I want to emphasize on. So you can think of this DER coordination problem. Basically, I'm trying to determine the reactive power for each inverter in order to improve the voltage profile of distribution system. It's a special instance of OPF in a way. Okay, so this is a simplified model that one can consider. So the objective is to minimize losses while making all the nodal-wise voltage to be within limit. So the constraints are voltage limits. And the Y here is the operating condition, basically the non-flexible load demand and all the input information. So we know that we can use what's called linearized power flow model to linearize the voltage constraints, and this becomes actually a quadratic program with linear constraints. But then the whole issue here is about the centralized solution needing a lot of communications, right? So basically, every node needs to update its operating condition. So for node n, it needs to update yn, which is like power demand, and all this information to a control center, and then they need to solve this. Although in a centralized location, it may be a very fast solution because it can be recast as a convex problem as shown here. But it requires very frequent communication, and this can change. And then the issue is in distribution systems, the variability is very large, especially with solar variability. So here's the idea of using ML. So basically, it's not what we have designed. People have looked at this from a couple of years ago from the list of literature you've seen earlier. So every node is using only local information and try to find this local neural net to predict local reactive power dispatch, okay? So the Y here is actually the input operating condition, and the Z here is the reactive power that it needs to predict. So the issue I want to emphasize here comes from the very beginning I told you about when we don't have the actual distribution, we use the average, the sample average to approximate that, okay? And this is like the last equation is the example of the average loss function that we introduced earlier. So this is the difference between the predicted solution from the neural net described by the function phi here, based on only local data, and then to the optimal solution that is solved, okay? So what is the issue on the average solution that we want to explore here is because, so here is a distribution of typical losses, like losses are non-negative here, right, with some kind of concentration in small values, and the average is somewhere the black line sits, okay? But what we care about a lot, as I mentioned, is like sometimes the worst cases, okay? In distribution systems, we care about the worst cases of voltage, okay? When voltage is within limit, I don't care so much whether it's 0.01 or 0.02, okay? But then when it's above 0.05, I want to really look into these worst case scenarios. And I know this is probably something you have heard in other contexts, the conditional value at risk, CVAR, can be useful, right? It's actually trying to characterize the worst case performance. And in a similar way here, I can use this on the sample losses and try to minimize or use it as part of my learning objective, not just the average loss, but then try to reduce the worst case loss here. So this is a risk-aware learning framework is generally about, and has been kind of picked up recently in the machine learning part. I think in the same way that we want the solution to be robust. So I don't want to spend too much time on this because I know that, in general, like a robust optimization class or like a work has discussed a lot about what is the reformulation for the CVAR matrix. And then what we really want to see here is like CVAR, when you use this for a training, has some kind of computation challenge, okay? So for the typical training, we use when you have average loss, and every sample would play a role in determining the gradient, right, in a average way. But then when you have CVAR, meaning you are selecting a small subset of samples, and which means that this gradient estimation will be worse, okay? We all know that there's trade-off between the number of samples to the value estimation.
Can I ask a question?
Yeah.
In the previous slide, you assume that you have this distribution, and it's gonna be the same. It will not be. It's not gonna change over your learning curve. So
It can change. It can. Yes.
So distribution can change.
Right. It's dependent on the input samples. because once like the current parameters change, right? So think about a neural net. Once the weight parameters change, then everyone's loss is different. So that's why this CY is a function of the parameters. Yes. So we are not like reducing the CY on the optimization variable per se, but we are reducing the CY for with the weight, the neural network weights as the parameters here, and that's why it's not convex anymore. So there is a little bit more discussion on that, but we just want to say that there is an acceleration part we did to try to work around the mini batch idea. So the mini batch here means that in typical machine learning training, you partition the data set into, say, multiple batches, and then you do the gradient estimation based on a subset, which is a batch, basically. And because of CY is a very hard to have statistical significance, it's only based on the worst case samples, right? So we only pick the batches that have a large enough CY value to do the gradient updates. It's like an adaptive sampling, but the idea here is just trying to be more selective. I don't want to use any batch to do the gradient estimation. Only when the worst case is worse enough, is bad enough, I will pick the CY there. Okay, I will pick them to do the gradient estimation. So there's a little bit behind this idea, but then I just want to quickly go to what we have done for like a distribution system, voltage optimization, and then comparing between the usage of MSE, or the average loss, which is the red line here, with the one that has the risk-aware, having incorporated the CY of the voltage deviation here. So what you're seeing here is the distribution of the voltage deviation for different samples. And without using the CY on the voltage deviation, you can see that the tail has the values above 5%. Okay, so this is where we mentioned about the worst case. But after incorporating the CY metric on the voltage deviation, we are able to reduce the worst case voltage deviation to be within the 5% limit. So it's not currently set up as a constraint optimization setup, because we just put it into a regularization term for easy of learning, but it's possible to do that. But basically, what we are exploring here is that by incorporating the loss function not in the average case, but instead the worst case, you can maintain the safety limits in a more ideal way. So this is the basic idea of the risk-aware learning part. Okay, so with that, we have like 2 problems with it. I know it was also a long intro at the beginning, so I hope that you have get a flavor like how you can use topology information of the grade to design a graph neural net to improve the model complexity. And then the second part, which was very short, I apologize, is on how you design the loss function, the measure of the performance based on the top samples, the worst case samples, instead of the average of everyone. That can help you to improve the safety of certain operation limits. So I think this is a good time for a break, and thank you all for this overdue, for this postponed time. All right, so I guess I'm in between you and the end of the day exciting social program. So I think the last part will be faster. So I hope you have a good experience with the direct end-to-end neural network now. So the last part is slightly switch gear on using reinforcement learning to look at dynamic resources. And then I think there was great introduction or background also provided by the previous talk. So I hope that it will be a quick one. So why do we need to use RL? So I always like the end-to-end learning when you have the samples that are just input, output, and that's it. It's like a static systems. But we know that's not always the case in energy systems. Some of them have a lot of dynamics, like when you look at storage or flexible loads, as in the talk. And also from the external inputs like price or weather, right? There's a lot of temporal memory. So these are like some selected profile from these inputs, and you can see the dynamics, the memory here. So when we go from static input-output to a dynamic systems, where the samples are based on the system dynamics, and that's why we transition from the private supervised learning framework to the case of reinforcement learning. So it has been advocated, say, in this recent tutorial, like we can use it for a variety of dynamic energy resources, especially those at great edge, because they are data-driven. They don't need you to build like a probabilistic model first. And they can also be adaptive, meaning that when you operate online for a while, it can learn from these online scenarios on what is the actual situation and be adaptive to that. So there's a good motivation on doing it. So what I will specifically talk about is to look at when we have abundant heterogeneous resources, and that increase the problem dimensionality, okay? And this affects the learning rate of RL. As we have heard earlier as well. So RL tends to be even slower than end-to-end machine learning because of this temporal dynamics. So we will see why we need like a powerful representations, like basically how to represent the system model in a certain way to make the learning more efficient. So I would like to start a little bit on the RL background. I don't know how much I need to get to it, but then just to set up the tone. So I'm sure you have seen this a lot, like usually the agent is the dynamic systems. As you learn in a typical control systems, this is your state space model or the plant, right? So the goal here is to find the policy mapping from the situations or environment or like what we call states to an action. So this mapping is similar to the functional mapping that you have seen in the neural network part or the supervised learning part. It can be a nonlinear function. So specifically, this mapping denoted by pi, so this is no longer the LMP, by the way, is a probabilistic distribution given the state, what should be the action be, okay? And we all know there's a objective here to maximize the total reward, and then subject to system dynamics as described here. And we could go over linear dynamics, have a nonlinear f of t as dynamics here, and the et is the random disturbance. And one of my favorite resource for RL is the tutorial by Ben Rapp from UC Berkeley, which connects the RL from a control system background. I think it's a short read, but very clearly written. Okay. So we know that usually we need to specify the Markov decision process, and that's the state action. So state is like the system state, or as in linear systems, and actions are the control, which we call AT, can be both discrete, either discrete or continuous. And the transition kernel is essentially like the system dynamics as in state space model. And the reward is related to objective here, is the payoff received, and then there's usually a discount factor between 0 and 1. And so this is kind of like adaptive signal processing. You use this gamma discount factor to indicate how much you want to include future rewards and instead of the current ones, okay? So there are a couple of functions that we define for RL, and then the first one is the return, is essentially this discounted reward at any time t. Okay, so this is starting from time t. This is your total discounted return starting from this time slot. And using that, we define this so-called value function. This is the expectation of that because you have randomness, perturbation. So that's why we have to have the expectation here to make it deterministic. Okay, so notice that this is a function of your policy, right? When you change how you design the control, like a feedback gain, for example, that can affect your objective as in linear quadratic regulator, for example. So this is the type of analogy here. So I just want to quickly mention that this V is a function of the policy, and this looking at a function of with the input of the state. So you can think of if the system is stationary, then you can start with any time t. And this would only depend on your current state value. It doesn't matter what time t you start this process. And this is the same for the action value function, the Q function here. So it is not just the state that you're currently in, it's also a specified action that I'm currently given. Okay, so that they're kind of like the counterpart. One is defined by only the current state, and then the other is defined by both state and action. So you can think of that there is some kind of relation in this Q function, because this Q function has some temporal dynamics as well. Because we mentioned if it is stationary, so it really doesn't matter which time t you start counting it or calculating it. So if there is a famous result which is basically we're coming from dynamic programming, is on the principle of optimality. So if you have this Q function and you started from time t, I don't know what's going on in this, there's nothing in the shaded part, by the way. Basically, when you look at the next time t plus 1 and you repeat this Q function, it helps you to capture all the expected reward from t plus 1 on. Okay? So there's a way to calculate the Q function at time t using all the future rewards starting from t plus 1. Okay? So essentially, in dynamic programming, which is a very powerful tool that we have used for solving unit commitment, I know many of you are experts on that. And in wireless communication, it's called weight-based algorithm, and it's invented by an expert, and he makes billions of dollars on that. By the way, he was the co-founder or the founder of Qualcomm. So that's why he's getting to be famous. But essentially, it is actually dynamic programming on using that for wireless decoding. And similarly, in speech processing, there's a concept called hidden Markov chain. And all of these are similar ideas in dynamic programming. And the most important results that we need to remember is that once we have the Q function defined for a given policy, they can be related by this Bellman's equation because of this principle of optimality, because the second Q function kind of captures all the future rewards starting from t plus 1, and then you can relate that from the reward starting from t using this additional reward at time t as well. Okay, so this is a short explanation on where the Bellman's equation comes from. So the other one I want to talk about is similar to the neural network where we talk about parameterization. This is the same thing here. We cannot search or allow the policy to be any function. Or we cannot say the Q that we want to find. The Q function can be any function that we want. So we use certain parameterized model to make the search more efficient. Okay? So this is very similar to the previous story about parameterize the function f earlier. So there one is to parameterize this pi, the probability transition, and you can think of it as, say, a Gaussian distribution, okay? So given the state, st, the mean is generated by a parameter theta times the st, okay? So this is one way to parameterize. This can be a continuous action. There are functions that you can use for discrete actions as well, okay? So this is to parameterize the policy. And the second part is to parameterize the Q function, for example, as Q that you're seeing earlier the Bellman's equation plays a very important role to characterize the optimality condition for these systems. So this is the famous deep Q network. I think it's the backbone of AlphaGo, basically. You use a neural net to say this is supposedly how the Q function should look like, okay? So that's another way to do parameterization here. But just very quickly about the different learning approaches. Under Bellman's equation, there is a quick way to update the Q. which is to say that because of this equation, as the last equation here, how do I enforce it? Okay, how do I make sure it is equality when I do iterative updates? So I use the samples to generate these differences here, and I use it to augment to my updates of Q. And that's the basis of Q learning. And if we go to deep QN network, it's also based on this Bellman's equation. It's trying to say that, oh, because these two paths have to be the same, so the square difference of them should be my loss function. So I'm trying to update this Q function, which is a neural net, to make sure that this loss function is minimized. So everything's about loss function, as we have seen previously. Okay, so this is a quick understanding of the Q learning. And the second approach that people do is direct policy search. Okay, so it's to say that now, while trying to reduce the total expected reward with discounting factor, it can be think of as a function of this parameter theta that I use to parameterize the policy pipe. And there's another famous result called the policy gradient theorem. It provides a quick way to estimate a gradient for this theta value from a trajectory. So long story short, you only need this G0, this sample reward, okay, with additional probability distribution information on this pi. So this pi theta is already given by your parameterized model, right? This part you already know. The only unknown part is this G0 from the samples. From the trajectory, you can compute that, okay? So this is the estimated version of your gradient, and then you can do favorite gradient ascent to solve this maximization problem, basically. So these are the basic ideas about RL, different approaches. I encourage you to go to the reference from Ben Wright about some more intuitive understandings. He didn't give too much math either, but then he explained also these methods from different angles related to control systems. It's a fun read. Okay, so I'm done with my short RL background setup. I'm gonna introduce this electric vehicle charging station problem, which I think is kind of a fun problem to consider, where dynamics of the great edge resources can be connected to reinforcement learning. So this is a parking lot for a charging station for EVs, right? So assuming that at every time t, there are EVs arriving, and then they have their remaining demand, and they have their parking time, right? That's what you submit to the operator, for example. So both of these quantities can be characterized based on the time. Like the demand can also be scaled to say, oh, how much time I need to charge that EV, right? So they're of the same unit, basically, the D and the P here, okay? So the problem for the EVCS here is to decide which EVs to charge, okay? Because the EVs have different priority. Some of them have more flexibility because they will park longer, and some of them are not, okay? So what is the key challenge here? Depending on the number of EVs, then you have this information on this remaining demand and the remaining parking time for each of them, right? So you have to include that in as your state, part of your state. And there could be many EVs, and each of them, and this number of EVs is also time varying, right? Because you have EVs come and go. Once they finish charging or they finish their parking, they will leave, right? And then there are always new EVs arrive as well. So this dimensionality is time varying, okay? And then the question we're trying to ask is, can we represent this state information, basically the remaining demand and the remaining parking time for each EV, in a certain way that bypass this dimensionality issue, okay? Because the basic idea of representation here is that, okay, let's say there's an image, okay? You have one angle to look at it, And if you change the camera angle, you look at it in a different way, but it is still same image. Okay? So the question is like, how do you want to look at these EVs in a certain way that helps your training process? So that's like the basic idea, like why I want to do a better representation. Okay? So what is the idea here? So let's say we have 4 EVs, okay? And then the P is remaining parking time. And so let's say they're all integers, like in terms of number of slots, okay? And the D here is the remaining demand, okay? And the idea here is instead of characterizing each EV by these 2 quantities, I'm going to use what's called laxity as the difference between the 2, okay? So assume some kind of homogeneous conditions on the EVs, then these difference laxity values here is sufficient to let me know how urgent it is to charge this EV. Okay? And therefore, we can group all these EVs based on their laxity. Okay? So first calculate laxity, so we can see that, oh, yes, the first vehicle has laxity 2, so it is urgent or not urgent compared to other with 0 or 1. It's less urgent, right? Yes. So I can delay the charging if I need to, if I want to, right? If I don't have, if the price is really high, then I can delay the charging for the first one, okay? But if 2 EVs, say the last 2, they have the same laxity, then their priority is the same, okay? And it really doesn't matter which one I pick to charge if I only get to charge 1, for example. So in this way, this representation from P and D to the laxity is a transformation. And furthermore, I can aggregate them. So I don't need to check, oh, what is the laxity for each EV? But instead, I'm only checking how many EVs are in laxity 0, how many are in laxity 2, how many are in laxity L for the maximum laxity level. Okay, so now I change the representation from the laxity for each EV to a fixed vector, fixed length vector, which is at most L plus 1 entries. For each laxity level, so this superscript there, okay, it indicates how many EV are there with laxity 0, how many have laxity 1, and so on. Okay, so that fixes the dimensionality issue that I mentioned earlier, because I don't check that for every EV. Okay, I only check, oh, what is the global picture about this charging station, right? How many of them are really urgent? How many of them are not urgent at all? And this is sufficient as in the last vector as a state here, okay? So the first one, the rho t here, by the way, is electricity price because we want the charging station to be responsive to price. So we also use that as an input state. So this is the basic idea of the representation here. So what are we able to claim? So don't look at this tedious algorithm. The basic idea here is that now I can do some efficient aggregation of the action as well. So let's say I only need to decide how many EVs am I going to charge in this time t. Okay, I'm not going to decide for individual EV. I'm only going to decide how many I want to charge in this time t. Okay, but then I need to disaggregate that or associate that. So say I can only charge 5 EVs at time t, but I have 10 in total. Then it's a good aggregation, right? It make my search easier, but then I need to have a way to associate this 5 EV budget back to the specific vehicles, okay? And this is exactly where you saw the laxity is important here, right? Then intuitively, I want to pick the EVs with very small laxity, okay? Because they're of higher urgency, okay? So very simple idea here is like, oh, once I have this total budget, I just need to go back to my parking lot, charging station, to see, oh, what is the laxity ranking of each of you, and then I'm going to pick the ones given my budget here. Okay, so this is the laxity-based reduction. So basically, now instead of deciding on which EVs to charge, I only decide on how many EVs I want to charge in this time. Okay, because I have this very nice way to go back to the specific EVs that I want to pick. Okay, and actually there's some interesting results that we're able to say that it can still maintain the feasibility because some kind of basically that by choosing the most urgent EVs, I'm not affecting the feasibility of this system. So yeah, there is a little bit more analysis on that in the paper. So this is on the action part. So now I don't need to decide on the action for individual EV. I only decide on the total number of EVs that I want to charge. Okay, so this is the action reduction. And then the state aggregation, which you saw previously, right? Instead of representing all the individual EVs demand parking time, I'm only capturing how many EVs are in this urgency group, or the laxity group, as I call it. Okay? So this is also an aggregation as well, because as I told you, this is not looking at the image from the front end camera. I'm kind of looking at it from a different camera angle in a way. But then there's a question, like, do I lose anything? Does that affect my representation power? Is that give me a tilted camera angle that I'm not seeing the full picture effectively? Interestingly, we were able to find that even with this representation, it maintains the equivalence with the private system under this so-called reward homogeneity and dynamic homogeneity condition. It's essentially to say that these original MDP will contain the same information as the new MDP that I just defined, okay? Because you can see that this laxity is really what I need to decide on which EV to charge, okay? So there's also more analysis on that, but then this equivalence is essentially to say that, oh, instead of representing every EV, I just need to know how many EVs are in this urgency group 1, in urgency group 2, and so on, okay? So this is our state aggregation part. With that, you can run your favorite RL algorithm. I'm not going to talk too much about that. We use a simple linear Gaussian policy, but you can use nonlinear or the powerful DQN, the neural network, to do that as well. But we show some more insight on this later on in numeric studies. But essentially, the basic idea here is this dimensionality issue has been very nicely addressed through my reduction of actions, because I only need to decide on how many EVs to charge at every time t, and also through the aggregation of states, because I no longer have this time-varying number of EVs issue. And earlier work has tried to do that with some kind of approximation, but then we will see that how really looking into the physics of this EV problem by designing this aggregation scheme based on the physics can improve over like a genetic approximation scheme for representation. Anyway, so actually I'm ready to get into the numeric tests. So this is an EV charging profile, the number of EVs that we got from some transportation studies. And then we look at daily charging for a 15-minute interval. So the total time horizon is 96 time slots. And then we use some real-time LMP price from ERCOT. So we have considered a few daily scenarios for training and a few for testing. So the comparisons between this representation based on the physics with a genetic approximation of the Q function to address the time-varying dimensionality issue. So I told you that I used the linear Gaussian policy, right? So essentially that's saying that, oh, the charging or the action is a linear transformation from my state. So as I said earlier, the states here are the price, the rho t, okay? And then NT to L, which is the number of EVs of laxity L. Okay, so we have at most 12 laxity levels, and this is the 0 to 12 states that you see indexed here. So why did we pick the linear one? Because we want to show that although we have to represent all these laxity groups, there are actually additional reduction possible here. Okay, so each of the values here is the parameter for each state. Okay, thinking about linear combinations of the state variables. Okay, if some coefficient's weight is 0, what does that mean for that state? Yeah, you don't care about that, right? Because it doesn't play a role to determine your output. Okay, so one interesting observation here is that the first two weights are much bigger than the others. Actually, there's a sort of like diminishing trend when you go to larger and larger L. Okay? So why is that? So when a EV has a very large laxity, meaning the parking time minus the demand time or the charging time needed is very large, we agree that this means the EV is not urgent, right? And they can, you don't need to deal with them now, right? So the larger laxity is, the less important they are to determine whether they need to charge or not. Okay, so we use this linear policy, and based on the weight parameters, you can clearly see that what really matters is the electricity price. Of course, we want to be price responsive, and also the most urgent EVs, like when the laxity equal to 0, meaning that they cannot delay charging anymore when laxity equal to 0, because your parking time is equal to the total needed charging time. Okay, so that's kind of intuitive. So maybe going further, we can do more aggregation. We can aggregate all the EVs above a certain laxity level, saying that all the EVs in the last row into another group, like not important group, or like the group that we don't need to worry about now, right? That's how we prioritize our work, right? There's always a deadline, so I tend to now just prioritize my workload based on what is coming up. So that's like essentially the same idea here, okay? So yes, again, we use the linear Gaussian policy to show this kind of intuition, but you're welcome to, we can totally use like nonlinear ones to make it more like prediction-wise more accurate as well, or improve the prediction, okay? Yeah?
That's a quick question.
Yeah.
I might have missed it, but so how do you ensure feasibility then again? Like if you're constantly lumping in these like low priority ones, like if you end up with just like low priority ones, how do you end up making sure that like if it's Markovi, like how do you actually keep track of that feasibility?
Yes, so good point. So the feasibility only can be ensured when we list all the laxity groups. So the results I had earlier about the feasibility only holds if we keep this structure. Okay, but if I do too aggressive aggregation here, I may no longer have feasibility. So this is like some kind of gap that we don't know, but we know that when this representation is accurate, we have feasibility, but not the other way. Yeah.
Gotcha.
Yeah, very good point. So there's still some theoretic value in keeping all the states, but depending on how much, how complicated, how many laxity groups that we want to model, there could be certain reduction, but it may affect some kind of optimality. We're not sure yet. Okay. Right. Good question. So finally, just some testing results. So we compare like what our algorithm to here with some kind of, as I told you, like genetic approximation called algorithm QE. It's a approximation for Q functions using certain fixed style of representation. So it doesn't incorporate this this laxity concept at all. And what we are showing here is, say, like a sample trajectory of the daily charging profile. with respect to the price. Okay, so I said this is for a day with 96 slots, and then we expect the price, which is the dashed green line here, have a peak in the afternoon hour, right? And what we can see is like once this peak starts, our method, the red line, because of the efficient representation, is very sensitive to that. It immediately step back, okay? And the jump from the post-peak time after the shaded area may not be ideal. So there may be some more work to try to think about how we can constrain the charging profile to be more smooth, to be smoother, because I guess that is something the grid operator also wants. They don't want everyone to start charging all of a sudden when the price begins to drop, right? So there may be something more to think about in the post-peak time. But what we are primarily trying to say that is because of the representation power, it makes the training more effective in identifying the key attributes to target on. And it can be much more sensitive to this price peak in order to reduce the total charging price. So we have some quantitative results to see that the charging cost has reduced on average like 4.2%. And this is thanks to the price sensitivity that we have here. Yeah.
In your stage, is it price for current point or also forecast?
Yeah, good point. So we only try to incorporate the current price.
Why not the forecast?
Yeah, I guess it's mainly a proof of concept. So we could incorporate instead of future price prediction, but past price. So that can help as a part of the state. So we can keep the price for the last, say, hour. That can allow us to see some trend of the price and be more prepared in a way. So I think, yeah, definitely our price, like the setup of the IL is not that robust, and there's something to work on that. Yeah, but that's a good point. Yeah. Okay. So I promise you the second part is gonna be short, because we don't want to break the computer for another time. So this is the end about the three problems that I talked about. So on the first one, we have seen how to use topology to improve the model complexity for OPF learning. It can be general learning problems. So I think there will be a lot of different use cases for a graph neural net in like large-scale power systems. And I think really the key is on the transfer capability, and I think this is something that graph learning can be unique at. And for the second one, which was real quick, we saw a little bit on how to use CY-based measure or metric to improve the worst case performance. And then we could think about actually for the mini batch selection method, we are working on the convergence analysis and other related to other safety guarantees. And for the last one, I think there's a lot of use case for RL at when we have small scale, like a different abundant and heterogeneous type of resources at the grid edge, and having this data-driven decision-making or policy construction idea would be very powerful to bypass the difficulty of requiring actual system model. So there may be, we have also worked a little bit on using RL for battery operation by considering the cycle-based degradation cost, and this is recently published in a journal paper as well. So I think there are a lot of questions we can all explore, and then the really key uniqueness here is like maybe it's not like a black box or like direct application. There are a lot more that we can say or we can think about, and from the power system or like the problem characteristics, or from our domain knowledge on where these methods can be better integrated into the specific problem. So I think there are a lot more that we can play here as the bridge between the methodology and the problem that we have at hand. So we'll be very interested to continue the discussion on what can be done in addition to these problems as well. So finally, this is a list of papers related, and since this is a summer school, I would also want to highlight a few educational resources that are related to data analytics or machine learning in power systems. So I have taught this graduate level course called Data Analytics in Power Systems at UT for 2 times, and the slides are all available in this link. And I have also tried to modify the slides in the second time, so it has more better consistency and in the second round, which was spring 2021. And right before pandemic started, we had a workshop hosted by US National Science Foundation on forging connections between machine learning, data science, and power systems research. And there are a lot of interesting talks from that workshop. I know there are a lot of more talks and themed workshops, sessions on these topics. So yeah, so these are always there were a lot of cutting edge research on that as well. And finally, I just want to mention we're also preparing some short courses based on the synopsis of my graduate level course, and this is funded by US Department of Energy to look at digital power system courses, kind of like a newer next generation power system engineering curriculum in the future. So we will post all the slides on that as well in future once this is done. And with that, I'd like to conclude the talk. I think, there are a lot of interesting problems at the interface of machine learning and optimization for the electricity infrastructure. So as we're dealing with how to harden the grid infrastructure, make it more resilient, as we're dealing with more and more system dynamics, resource dynamics. And also, I know natural theme is like when we have less and less understanding about what the actual system model could be, or there's certain variability in the actual system model because we have new type of inverter-based resources or different heterogeneous type of components. So I think there are a lot of more questions and open questions and also problems on this. Be really interested to talk to you more on that. So yeah, feel free to send me an email or like or we'd love to continue the conversation on this. And with that, thank you all and have a nice afternoon.